actually have it virtually up here. Okay. All right. So here's the warm up. It says, oh, the light in the back is off. Oh no, it's not. It says the highest possible y value for a point x comma y on the region D that I sketched for you here is always the same. Do you agree or disagree? Think about it first by yourself, and then I'm gonna have you share out with a classmate. Okay, you guys can chat. Jacob.
The same as what?
Whatever you think it means. No, that's important because that's actually part of the warm-up. Okay. So the highest and lowest possible y value for a point xy on the region D is always the same, meaning the y value is always going to be the same. Okay? But whatever you think that means. So think about it. And I just realized I need an actual ruler today. So let me go look at another classroom to see if I have a ruler. Think about it. Think about it.
I was thinking of this as like the domain of well, regardless, the highest, if it means the same as in the height of the lowest are the same, I think it's just possible. Because there's going to be a highest point, because it's going to be a boundary. Not infinite. It's going to be a highest point. But it's more specific.
Yeah, the line,
not just for
the
region, but for a
That's been known for the past. All right, yes, thank you. Check in with your classmates.
It didn't sit right for me to go. I got like a headache. Like your head. I started like.
All right, guys, let's see what's up. So let me hear from, I don't think Garrett's here. Jacob, what do you think? Did you agree or disagree?
I'm not so confused, but I think I disagree because
The width, you mean like this part right here?
yeah.
Like the thickness, is that what you mean?
Yeah.
Okay. Okay. Okay, all right. All right, good. Let me hear, thank you, Jacob. Let's see, Cesar, what do you guys say, you and your group?
I disagree, because in the region, the highest y value would be 5, the lowest would be 1.
Okay, so you're saying that it would always be the same, right? Okay. But you did add a little bit more of a specific value. You said it will or won't always be 5.
The highest y value would be
5.
5.
Okay.
No, I can see on the graph.
Okay, sweet. All right, so I needed this for a ruler, okay? This is what I need your guys' brains to do today. So the ruler will either be facing vertically, parallel to the y-axis, or the ruler will be facing horizontally, parallel to the x-axis. What I need your brain to do is I need your brain to move this imaginary ruler on this region. Okay? So for example, if I place the ruler where x is equal to 3, right, and let's say I wanted to measure kind of like what Jacob said, the thickness, right? I guess what would be the smallest y value where the ruler is placed right now? If I was to measure this, it would go down to where? It's like 1.2-ish or something, right? And what would be the highest y value that I would measure at for the thickness? 4 point something, right? That's when the ruler is placed at x is equal to 3. But now if I place the ruler, let's say at x equals 5, what's the highest y value that I would have to measure up to? It's like 4.8-ish, right? Is that the same y value that was measured when it was at x equals 3? It was different, right? What about the x value? Would it be the same? Close, but not the same though, right? A little bit different. But now, when I move my ruler sideways, up to what x value can I move my ruler? 6 and 1, right? I can't go after that because there's no more region. Okay? So notice that my ruler is going to move only between the numbers 1 and 6. But as I do that, the ruler, when I measure the y value, the highest y value it'll be is according to the curve that's bounding it up here. Okay, see that? And the lowest it could be is going to be bounded by what? The curve that's bounding the region below that. You see that? Okay. Now, is it true that the highest y value will always be 5? That's the maximum y value out of all of them, right? But according to my ruler, this will never reach 5. You see that? That's the difference. Yes, y equals 5 is the biggest, but depending where my ruler is at, that y value, that one right there, which is not 5, that's the biggest. That's the difference that I want you guys to take from this. Okay? Yeah, check.
I guess this is kind of like a trace in the x direction, but it's only 2 dimensions.
A trace in the, say that again?
It's a trace, but it's only 2 dimensions.
Oh, I get you. You like with the ruler?
Yeah.
Yeah, that's right. Yeah. Exactly. Like, you guys ever play that ice hockey or the air hockey game in the arcades? So it's like if I got the ball of the air hockey here and I flicked it so it goes up and down, the highest the ball will go is bounce up to here to this y value bounded by this curve, and the lowest it'll go is down here bounded by this curve below, right? If I flick it, if I place the ball right above x equals 4, and then I flick it, it'll go like that. Versus if I did it like right here at this x value, then it'll only go up to there. The ball will only bounce between those two. Okay? Okay. All right, so let's see. How is this going to tie into today? Let's see. Questions about the warm-up? You guys kind of visually see that visual? Okay. So for today, either picture the air hockey ball or picture the ruler and you're moving it. The ruler, you're looking at how it's measuring the bounds between y, the upper y and the lower y. But as the ruler moves throughout x equals 1 to x equals 6. Okay? All right. All right, so let's see. Turn in your homework before I forget. Turn in your homework. I forgot to collect that homework. I got so worried about the ruler. Forgot all about your homework. Takes the mask off. That's what you're referring to, right? Scooby-Doo. And then during the break, I have hella homework to pass back, so I'll pass it back. And now I got a stack. I was waiting for me this weekend. It was a depressing weekend. The Niners lost right as I was grading.
It was kind of fun, even as a Niners fan.
Come on. Yeah. Okay, let me see. I can organize this.
Browns are so bad.
All right. Anybody need this packet with all the visuals? Not take it out, please, okay? All right, so let's see what we're gonna do today. So section 15.2, double integrals over general regions. All right, so we're gonna go off of what we did on 15.1, which was rectangular regions, okay? So let me show you what I mean by general region. So for a general region B, we'll enclose it by a rectangle R. Let me see, do I have that picture? Yeah, so if you guys look at that first visual there, you have your general region. It will be some shape like this. This is what we're going to call B. And then we're going to enclose it by a rectangle we're going to say that rectangle has x going from A to B and y going from C to D. And so this is a rectangle R that we look at. Okay. And so to help us integrate a continuous function f over this region D, we first define a new function f on the rectangle. Because on 15.1, we know how to differentiate a function over a rectangle. Okay? So this is what we're going to do. We're going to use this arbitrary continuous function f. And we're going to define it as a piecewise function. So that it'll equal little f if that point that you're plugging in is in the region D. Otherwise, it'll just be 0 if it's not in that region. So let me get the visuals real quick. Careful. Give me 1 second. So here's the graph of f, right? Let's just pretend this is a graph of f. It's defined over D. But then we enclose the graph of D, this region D, by this rectangle. And so then the graph of f, for all the points that are on D, is just the points that correspond to little f. But every other point that lies outside of D, you plug it into capital F, and it just gives you 0. So it'll lie on the x vector. Okay? So what I would like you guys to notice is that if we were tasked with finding the volume of the space between the graph of capital F and the XY plane, the part outside of D, the volume is just 0 because it's flat on the plane. So the only part that will give us positive volume is this part right here, right? So notice that the volume of the surface of capital F and the rectangle is the same as the volume of the graph of little f and region D. So it's kind of like a trick. We're doing a little trick here, okay? Jacob, question. For regions, well, we'll see. We'll get there. Later on, we're going to describe this region D. Yeah, right now it's just arbitrary, like general. It's like a general region. Yeah, but we'll get there. All right. All right, so let's see. So how are we going to do this? So using this new function f, capital F, we have that the double integral over the rectangle of capital F, which is what we learned how to do on last week, 15.1, that volume is the same volume as if we try to find the volume between the graph of little f and the region D. Since they result in the same volume. And then here is that visual that I was showing you. Okay, so that's kind of like the idea. That's how we're going to do this. Now, to Jacob's question, what is this D here? What is this region D? So what we're going to do is we're going to actually categorize a general region. We're going to categorize it into two different types. Okay. So to continue, we'll need to categorize a general region D into two types. And this is where the warm-up is going to come in. So type 1 is where D is a region bounded, not bounded, a region between two functions of x. Two functions of x. And if you guys look at your packet, I believe your packet has it. Let me see. Oh no, it doesn't describe it. So this is how we're going to describe the region, okay? We know it lives on the xy plane. Lives on the xy plane. And let me show you the visual. Let me go to that picture real quick. This is what it's gonna look like. Let me move it over here. Oh, I'm running out of space. There we go. Okay. So it's gonna be between some graph bounded above. This is the whole ruler thing, the whole thing I was mentioning in the warm-up. And so if you put the ruler at a particular x value, notice that it's going to be bounded above by the curve of the function g2 of x. That the highest the y value will go is depending on that function, the output of that function. The lowest it'll go depends on the bottom function. You guys kind of see that, like how we did on the warm-up? So that's my ruler. Depending how I measure this, the top will always go up to whatever G2 is, and the bottom will go to whatever G1 is. But now, between what two x values can I move the ruler? Between A and B. My ruler will only slide between A and B. And so, oh shit, it's like fucking Inception. Okay? And so we're gonna describe it this way. We're gonna say, this is a region where X is gonna travel between A and B, but the Y values are gonna be bounded between the functions G1 and G2 of X. Like that.
How many types are there?
Two. Oh, it says right here, 2 types. We're gonna categorize it into two types. Okay? That's G1 of X and that's G2 of X, correct? Yeah. So I want to leave a picture of that region there so you guys can see it. Okay? All right, so then let's see. So how exactly do we go about then doing this integral that we were saying that these are supposed to be equal? Okay? So let's see. If we have a region of type 1 that is bounded in this manner, I don't have a room here, I don't want to do it here. So notice that if we try doing this integral here, we said that this integral gives you the same volume over R and capital F. Capital F, though, is defined over this rectangle. Right? Defined over that rectangle. So let's use what we learned in last week. How can I rewrite this double integral using the bounds of my rectangle? Let's say I want to do remember Fubini's theorem says I could do dx first or I could do dy first. You guys pick for me. All right, let's say we're going to do dy first, and then dx. What would I write here? Y goes from C to D, and x goes from A to B. Okay? But since the output values of a function are going to be 0, if y is less than g1 of x, right? If it's less than g1 of x, so it goes below, that's going to be 0. Or if the y values are greater than g2 of x. Then we know the functions is 0 there. Okay? So here's what's going to happen. So then what we end up getting is that this original integral that we're trying to solve for, which we showed equal this double integral with capital F, here's the new part. Y will no longer, the highest y will go is not d anymore, because anything above d will just produce an output of 0. So what's the highest it'll be then if it's a type 1? It'll be whatever the y value is on g2 of x. So we're actually going to rewrite it like this. We're going to say capital F of xy. If I do dy first and then dx, y will actually go from the lowest it'll go is the g1 of xy value, and the highest it'll go is the g2 of x value. and where x will still range from A to B. Since D is of type 1. One more equal sign. Yeah, Charlie.
In this example, you have A and B, the lines aren't touching the region D, but in the visual example, it looks like the boundaries are cutting it off.
You're right. Sorry. We're gonna enclose it in a way so that the x values are the same. Thank you. Pointing that out. So do you guys see these bounds here? These bounds will guarantee that all these points x, y lie on what? It's going to be in D, right? All these points will now for sure lie on region D. And capital F for points on D just equals little f. And so therefore I can change all these output values to just little f now. dy dx, where y will be bounded below by g1 of x and bounded above by g2 of x. And x still goes from A to B. And so if we put all this together, that means that when you're integrating a function over a region of type 1, what we can do then is you're going to have to figure out what's my upper bound function for y, what's my lower bound function for y, and x will go between A and B. And so what I want you guys to notice is that now your endpoints are not numbers. Now your endpoints are functions for the first variable that you're integrating. That's the new part. So when you get to integrating, that's going to be weird because you've never done something like that. You've never had an integral where your bounds are functions. You've always had it where they're just numbers. Okay, so when we have a type 1 region, this is how we're going to construct our integral. So let's take a look. Let's look at an actual example so you guys can see what that's going to look like. We'll break it apart, ask questions, and then see what's up. So homework will look something like this. Evaluate the double integral where the function is just x squared plus y squared, where D is the region enclosed by y equals x squared and y equals 2x. So let's see. So we got to know what the region looks like to begin with. Okay? So is this region a 3D thing or a 2D thing? It's 2D, right? It's on the xy plane. So let's see. So let's sketch first. Let's sketch D. There's x and y. Y equals x squared. That's just a nice little parabola. And then we got y equals 2x. Actually, let me not be sloppy, hold on. Let me not be sloppy. Sorry. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let me put some increments here. All right, let's do this again. So the parabola will be 1, 2, 4. So the parabola will look something like this. Right there. Y equals x squared. And then you have your line, which has y-intercept 0, slope 1, 2 over 1. So it'll be this line right here. Y equals 2x. Starting to feel a little Calc 2-ish. Okay. So what's the region enclosed by D? What do you guys think that's describing? Sorry, what's the region enclosed by these two?
That first quadrant right there.
Yeah, it's this little bad boy, this little slit right here. Okay, so it's this little guy. All right. Is it of type 1? Throughout the entire region, is y bounded above by the same curve? So if I do my ruler here, is it always going to be bounded above by the same curve when I measure the thickness? This will always be its upper bound right here, right? So actually, let me go like this. Let me do this. Notice that if I draw little arrows going up like this, it's always bounded above by which curve? 2x. So notice that y is bounded above by 2x, and what's it bounded below by? It's bounded below by x squared. So my ruler will always be bounding between those two, but from what x value to what x value can I move the ruler? You would have to figure out that point of intersection, right? So point of intersection. How can we find that bad boy? Set them equal to each other. Do a little factoring here. You get x is equal to 0, or x is equal to 2. So 2, 0, right here. Okay? So yes, 2 right here. So then you have that x is bounded between 0 and 2. So it is indeed a region of type 1, like in this manner. So if it's a region of type 1, that means that we can, to evaluate that double integral, we're gonna have to write it out as a double integral with those new bounds. So this tells me that the double integral that I'm being asked to find, y is bounded below by x squared, y is bounded above by 2x, and then x is bounded below by 0, and then by 2. Like that. Okay? So then it's gonna feel like what you guys did in 15.1. You're gonna have to integrate this function partial integration with respect to y. Okay, so let's just do that first. Let's do that step first. So let's leave the x part outside, and let's do the inside. So can you guys help me integrate this function with respect to y? What would this one be? X squared is a constant.
X squared y.
X squared y plus
1/3 y cubed.
1/3 y cubed, evaluated where y is x squared and y is 2x. So instead of numbers now, the bounds are functions. So that's where this is new. So what do you think we have to do? Plug them in anyway, that's right. Okay, but you're gonna plug in functions, Jacob.
Yeah,
Okay.
they'll just result in the function as one.
And then, exactly, and then everything will now have an x. Yeah, that's exactly right. So we plug this in here. We're gonna plug in all the 2x into all the y's. So it's gonna be x squared times 2x. Let me make it, let me color code it here for you guys. 2x. Plus 1/3 2x cubed. So that's the first part. And then you have to plug in the x squared. X squared plus 1/3 x squared. Oops. X squared like that. I'll save some of the work. I already did that for you guys. I multiplied everything out, combined like terms. So you multiply all this garbage out. I know. You combine like terms, and then it becomes an annoying Calc 1 problem. So when you combine everything, guys, you're gonna get 1/3 x cubed minus 1/3 x cubed. Sorry, x to the 6th minus x to the 4th plus 14/3 x cubed. No? So then it becomes a Calc 1 problem. I did that work for you as well. You integrate all of those, dot, 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 and then you get 216 over 35. But this is the new stuff, and the new stuff is this part right here. These two steps here. Going from here to here, going from here to here. Yeah, no.
Would you do the same thing like with sideways? Where you integrate like x first and the bounds would be constant for y?
That's gonna be type 2.
Um,
Yeah, we'll do that in a little bit. Yeah, so that's actually some comments I had. So remember Fubini's theorem so that you could just swap the bounds? Here, if I was to swap these bounds, now my bounds outside are gonna be functions. So will my final answer give me a number? No, right? So what I want you to be careful with is that for general regions, you can't use Fubini's theorem. Okay? So Fubini's theorem does not apply for general regions. But what you could do is what Noah was mentioning. Okay? Yeah.
I was gonna ask if you were swapping, could you just change the x with function of y and y with y?
Exactly. So sometimes, as you guys were noticing when we were doing problems in class, it's helpful to swap because maybe you can use a u sub versus if I can't swap, then I have to do trig substitution, for example, right? Like nobody wants to do that. So it'd be helpful if there's a way for me to swap the order of dx and dy. But as both Noah and Sam are mentioning, to do that, we're gonna have to figure out bounds for x as functions and then let y be constants. Okay, so yes, you guys are right. That's gonna be the goal. That's gonna be the goal. You guys are right on the money. And so let me just show you the visuals so you guys can see it. So this is type 1 that we just looked at. And so yes, you guys are right. What we're going to want to do now is we're going to want to do a type 2 problem. Is this type 1? That's type 2. We're going to want to do type 2 where you're going to bound y by some values and then x by some functions. So that therefore now I can do dx dy. Okay? Okay, so yes, let's work that out. Let's see how that works. So let's define a type 2. Type 2, so D is a region between two functions of y. And so the way it's going to look, it's going to contain points where now y is going to be bounded between C and D. And then we're going to call the functions for x, we're going to call them h1 of y and h2 of y. And I just realized I don't think I have it. Oh yeah, I do have a picture for you guys there. Yeah, I do. And so it'll look something like this. Okay? It's exactly what you guys predicted. So now your ruler is going to be horizontal, facing the x-axis. And so as I move the ruler can only move between C and D. And as I measure x, depending on the y value that I'm at, the biggest x value will be determined by this function h of y, and the biggest y value, smallest one, will be by h of 1, and so on. Like that. Okay? And so all this work will look exactly the same. Okay? All this work will look exactly the same. And so we have that if D is of type 2, and I want to find this double integral of some function, my task now is f is going to be bounded between, we're going to integrate with respect to x first, but now x will be bounded by these two functions. So the smallest it'll be is h1 of y, h2 of y, and then now the bounds for y are going to be c and d. So here's what I would like you guys to do. I want you guys to do this exact same problem with this exact same region. Notice you can think of it also as of type 2, where instead of bounding y, I can bound x instead and go sideways like this. Right? So now I want you guys to determine what would be what would be the h of 1 curve that bounds x below, and what would be h of 2. If you're told that these are the equations of it, of those curves. Okay? So practice. Using the same region D in our previous example. Set up the integral. So D is of type 2. So here we set it up so that it was of type 1. That's what I mean. All I want you to do is figure out what is the integral going to look like but if you're thinking of that region of type 2. Okay? Let me have you guys think about that for a bit. It might help if you guys can organize it like what we did here, but do it so that it's organized so that it's of type 2. Okay? What is X in between? And what is Y in between? Okay, let's do that. I'm going to pass back homework. Ethan. Careful. All right, guys, just check in with your classmates real quick. Check in with your classmates, see if you guys agree with bounds. Take a look at each other's work real quick. All right, go. Do a quick check.
Yeah.
Oh, yeah. Sorry, 2 3. And then I just got
2 came
zero.
from the 1/2, I just multiplied it.
Isolate X and Y equals 2X. Or X. Again. Y over 2. I got 4 for that. Between 0 and 4. So I just plugged in the X values that we got there. And then this point of intersection would be where X equals 0 and X equals 2. So I just plug in those values.
Yeah, that's where I was going first, but then I looked there and realized it is not X4. I just have to back in.
Is it not at 4?
That way.
Equals 4.
5 is the top of the that's like 3.
That's the math. What you plug in the X, get the Y.
This says, it's a 1/2 y is equal to,
Most of the time,
The other variable.
most of the time is, that's what it is. Everyone in
So
small
if you're like,
regions,
if you're like
zero
evaluating that,
to
the value.
Israel.
The rest of it is like a value.
Okay, guys, let's take a look. So when you're bounding x here, what is the smallest x could be? It's bounded below by which curve? The line or the parabola? Below, right? Bounded below by the line. And so you have your line here. You have your line, but you need to have x being isolated, right? So you have to get x by itself, which gives you 1/2 y is equal to x. So this line, I can rewrite it in this way so that I can think of this line as a function of y. So that's your h of 1. So that's what x is going to be bounded below by. And then it's bounded above, all the way to the right, by the parabola. And so since the parabola is given by this quadratic equation, I have to write it in terms of a function of y. So you get plus or minus square root of y is equal to x. But which one do we choose? You're going to choose the one with the positive x's, right? So positive square root. And so then x is going to be bounded above by the positive square root function. Oops. So this is the h1, this is the h2. And then my ruler will go from 0 all the way to that point of intersection, which we know happens at x equals 2. So what's the y value of that point? My graph is hella not to scale. It should really be at
4.
It should be at 4, right? You plug in 4 into 2 if you plug in 2 into these, y will be equal to 4. Yeah, so y should be bounded below by 0 and by 4, giving you this integral in this manner. If you didn't have to compute it though, but if you did compute it, meaning if you actually did partial integration, plug in these as your bounds, kept going, you're going to get this answer, 216 over 35. Those will be equal. Those will be equal. So this integral here is going to be the same integral as when you bounded y by, what did we do first? We did x squared and 2x with the same function. So here's where you got to be careful, okay? Like you guys were noticing. If I want to switch my integration order, it's not as simple as just moving these like I did with Fubini's. You have to reassess the region and rewrite it as a type 1 or type 2 so that you can see how do you manipulate this. All right? Questions? Are you guys okay? Are you having a good time bounding the functions? That's the hard part. Right now, I'm taking you baby steps, so maybe it doesn't seem that hard, but let's do a more complicated example, and then we'll see how you feel. And then I think from there, we might take a break. Yeah, we might take a break. You guys are hella low energy. Am I the only one giving you an exam this week? No, I see a lot of no's. Crap. Okay, so that explains the energy in the room.
it's exam week.
It's exam week. I never liked those weeks. Sorry. Okay, so I want to look at more complicated example. Break it apart, ask questions, and then we'll take a break. Okay, so this problem is considered an easier one because it already kind of told you which function to integrate. Okay, and it kind of gave you some idea of what the region looked like. Okay, so the ones that are considered more difficult are the ones where it doesn't tell you what to integrate, and it doesn't really describe the region. You have to figure it out yourself. Okay, so let me show you. So here's an example question. It'll say set up, and we're not even going to integrate. It's just the setup that's going to be the hard part. Set up the integral that finds the volume of the solid enclosed by the cylinder's z equals x squared plus 1, y equals x squared, and planes z equals 0, y equals 4. This is the example problem where I told you guys chapter 12, quadratic surfaces and all that. This is where it's important. It's these type of problems. Okay. I don't even know what type of region I'm using. I don't know anything. I was told all this crap here. And I gotta figure it out. So here's some hints, okay? Start by figuring out your region first so that you can determine if it's gonna be of type 1 or type 2, okay? And the way you wanna do that is, let's sketch your region D. Any equation that does not have a z in it, you can graph it on the xy plane. So start by graphing equations that do not have any z's in it, okay? So I'm gonna write some of this stuff down, okay? Because these are tips I was told when I got evaluated. You say them, but you don't write them. Graph any equation without a z coordinate. So let's see. So I have y equals x squared. That does not have a z coordinate. So I have y equals x squared. That's just a parabola. What else do we have? Y equals 4. 1, 2, 3, 4. So that's just a nice horizontal line. This is y equals 4. Okay. And then sometimes you want to graph equations that do have z in them, but on the xy plane, what is the z coordinate? It's 0, right? So let z equal 0 for those equations, and then see if you can graph whatever's left. Okay. So graph equations with a z coordinate, but let z equal 0. Sometimes that will be helpful, sometimes it doesn't really give you anything. So I have this equation here where z is equal to x squared. So I can let z equal 0, and then see if I can somehow graph this stuff. Let's see. What happens if I try solving for x here? Yeah, you get like imaginaries, right? So so there's no solution here. So there's nothing to graph. Okay, there's nothing to graph. And if I let z equal 0 here, I just get 0 equals 0. That's nothing to graph either. Okay? Versus if this was to be like z equals x squared minus 1, right? If it was minus 1, I would have ended up with positive 1 here, and then I would have got x equals positive 1 or x equals negative 1, which I could have graphed like this. You see what I mean? So in this case, this second point here didn't really give me anything, but sometimes it does. Okay. So this is my region. You guys see the region here? This is region D. What do you think? Type 1 or type 2? What would be easier to do? Type 1 or type 2? Yeah. I could do type 1, where now y will be bounded above by which curve? Y equals 4, and then bounded below by x squared, right? So if I do type 1, I have that y is going to be bounded below by the parabola, and by y equals 4 on top. And then my ruler here, my little stick here, will move through which x values? You would have to figure out these x values here, right? When does this function equal 4 for y? 2 and negative 2. Okay? So I know how I can use this to set up my bounds now. I'll be able to figure that out with this, for type 1. But now the question is, what's the function I'm integrating? Okay. Maybe this one, right? Maybe this one. But here's where you got to be careful. Sometimes the surface is below the xy plane. Sometimes it's above the xy plane. And that will matter, okay? You won't always have to do this, but since you guys have a tool of GeoGebra or Desmos, just to confirm it, you can graph things, okay? So let's just do a sketch of the surfaces here. This is the part that's kind of hard, okay? Where you have to use some of your chapter 12 knowledge. In 3D here, let's see if we can figure out maybe like what's happening here. Remember, these are cylinders that we covered in chapter 12. Do you guys see how this first equation is missing the y variable? So when you had a free variable, you guys remember that the cylinder just was parallel to the axis of that free variable? Okay. On the zx plane, what does this graph look like? Parabola shifted up one, right? But it's on the zx plane, right? So on the zx plane, I have like this parabola like this. Okay? But because y is free, that parabola goes parallel to the y-axis, so it looks something like this. It looks something like that. Okay? So you have like this like folded sheet of paper like that. Okay? Then we have this other cylinder. What variable is it missing? Z. So on the xy plane, that's just a parabola, right? It's this parabola that we graphed. On the xy plane, that parabola opens towards the y-axis. Let me use a different color. So that parabola is going to open like this on the xy plane. You see that? Here's where it's going to get weird, okay? That parabola is going to shoot, what's the free variable here? So it's going to shoot towards the z-axis, up. And as it does that, it's going to intersect this other green cylinder. And that's the part that's hard, okay? What the hell is that going to look like? And that's the hard part, okay? So notice that because of the curvature here, it's going to kind of do this like funky thing like this. It's hard to see it. It's hard to see it, okay? It's going to kind of like twist towards us like this. Then there's the plane y equals 4. Let's say that was right here. There's that plane. There's this plane right here shooting up. And then you got your z equals 0, which is just the xy plane. So it's a lot going on, and it's very visual. So what is this solid that they're talking about? What do you guys think? Let's kind of see shape. Let me see from here. You kind of see it. So it's going to be this solid right here. It's this guy, this, and then what's happening is that this is going to intersect this. It's going to intersect it like this. Like that. It's like this weird this weird solid inside of here. You're like inside of this point, inside of this thing here. Okay? And so it's like, it's this part here. That's as far as it goes. And the farthest back it goes is here. And if you're inside looking up, what are you looking at? If you're inside looking up, which graph? What color? You're looking at the green stuff inside of it. Okay? Jacob, did you have your hand up? No. Andres, what's up? Yep, I'll show you decimals. Yeah. Let's see. I had it ready for you. That's just how it takes so long. Okay. So here, yeah, let me go like that. The green is the same green cylinder, right? That I sketched there. The purple is the one that was going up. So you guys see this little region right here inside? It's hard to see it. But being inside here, that's the solid. It's this part right here. Okay? Now, you don't have to always have a perfect sketch. What's important, stop moving. What's important for these problems, guys, is you guys understand what you're finding the volume between the XY plane and the surface, right? So what you guys just need to understand is what's the surface, right? You guys told me the surface above is the green one. Most of the time, the function is the one that has z isolated equaling a function of x is 1. Most of the time, okay? And so if you guys look at these equations and you put all this together, you say, okay, the green guy is z equals x squared plus 1. This is my f of x, y. Okay? That's your f of x, y. And so when you put all this together, this is my region B. And I'm integrating a function. I'm doing type 1. So what you guys will have to figure out is what's f. In this case, f is this function. And we did type 1, right? Type 1, so it's dy first and dx. And then you got to put this together and say y is bounded below by x squared, above by y plus 4. And then x goes from negative 2 to 2. Yeah. The purpose here is that sometimes when you graph an equation that has z in it and you let it equal 0, you'll be able to graph that on the xy plane, and that'll describe your region B. In this case, it didn't give you anything. So it didn't give you. On this side here? Yeah, so it's like, let's do that. So it's kind of like
force you to continue. Would it be possible to say that one more time? The last part? You would have somewhere need to know that y is x squared. I guess, yeah, that you're gonna plug that in anyway. Yeah. But remember, right now it's not that bad because this is just a constant with respect to y. Oh, it was more challenging, right? Than the other one? All right, forgive me. You need the opposite of it. You need a picker upper thing. So let's take a break. Come back at let's say 2:15. I'll give you guys a longer break. So resume at 2:15. Coffee. Have you guys tried those the frozen ice cream things that they have at the bookstore? The milkshake things. You should check them out. They're hella good. Yeah, they're hella good. Yeah, you have enough time, unless the high school student. Let's resume recording. Okay, so I'm going to leave this problem here. I'm going to give you guys your own problem that I want you to work out. So let's do this practice problem here. Try to work it out with your classmates. If you want to use GeoGebra or to help you out, just do that, the beginning part. Notice this is just the setup, okay? We actually didn't finish the integral. Set up the integral needed to find the volume of the solid enclosed by the cylinder y squared plus z squared is equal to 4. Planes x equals 2y, x equals 0, z equals 0 in the first octant. In the first octant. Okay? Yeah, first octant is where x is positive, y is positive, and z is positive. It's the one facing us, correct? Yeah, the way we draw it in the math class. And so yes, try to do sketch the region D first, and then try your best to see if you can have an idea of what the surfaces look like. To at least figure out what the function is that you're integrating. Okay? Keep in mind these tips that I gave you. Keep in mind these tips. They're very helpful for these ones.
How would the rest of them be numbered? Like, I assume 1, 2, 3, 4 would be like normal in the backside.
From me looking that up, there's no convention on how they're numerated. So it's like, I guess we could do this, like maybe do the way we do with quadrants. Do like 1, 2, 3, 4. And we start with that from 1.
So in the first octant itself is kind of arbitrary phrase, that's the only one.
It's yeah. Positive octants, maybe better name for it. they will never tell you like the third octet. That will never, they won't say that. All right, so try it out. Maybe when you have an idea of your region D, just check in with your classmates, see if they have the same region. So now my tips were graph any equations that have no z coordinate on them on the xy plane. And then if an equation does have z in it, set it equal to 0 since you're on the xy plane, and see if that produces new curves. Yeah. And then do some highlights. If you don't like art, then focus on the algebra. That's the outcome. These practice getting region D, it's going to get harder. So it's a good habit to just kind of have that idea of the region. It's going to get harder as we go on. Once you sketch a region, then you have to decide, do I want to think of it as a type 1, type 2? Don't forget that the first octant is where x is greater than or equal to 0 and y is greater than or equal to 0, okay? This statement? And z, yeah. And z. But this is going to help you when you're doing your region. All right, can I have you guys just share your work real quick? Just share each other's sketches or what you have so far. I'm seeing different regions. I'm seeing you guys doing different regions, so I want to do a check in here. Is it cool if I have you move here? Just so you can work with Marco?
I tried drawing this part and then ended up doing the outside curve backwards. It's like one was this way and one was that way. I was like, oh my god. I wasn't sure how that second line there.
Try sketching it
Oh,
just
yeah.
Go around, let me know if you have questions.
Yes, that the actual line was in my head, 1/2.
There's only one equation. Yeah, there's only one equation.
This is like the rough outline of what I have.
Which just means that form x, y, unless you do zero.
So yeah.
Zero.
Equation with the z equals z equals zero.
That's kind of like a picture we have
And then it'll be plus or minus, but since it's just yeah, I drew like however, so I go, hold on, it's gonna be you can see my life before, that's why. And then I drew, and then I went, maybe if I balance. No. Here, the lower bound. It's actually not that bad. Yeah. Actually, so that'll be what Z is. So yeah, the equation you're actually integrating is going to be Z equals and I did.
Guys.
X 等于0 ，Y 等於 Z 即係X 等於0，Z 等於0，但係正語嗰邊咧就係 X 等於2Y 咧，佢就係其實應該唔同。
All right, guys, let's see what's up. So I hope you did try to sketch the region D. It makes it a lot easier to kind of figure out what the hell's going on. So let's start with just that step. Let's sketch region D here. And remember, you're going to do that on the XY plane. I'm going to make it nice and big so that we can really annotate it. Okay, so I'm going to start by graphing all equations that just have an X and a Y. And it looks like it's just these two. Okay, so I have X equals 0, which is just the Y-axis. Right? And then you have this line here. You can rewrite it if you want as 1/2 X is equal to Y. That way you see that it's just going to go. It's a line with slope, what is that, 1/2? 1/2, y-intercept is 0, 0. So it goes 1 over 2. So it's going to be some line that kind of goes like that. So there's this guy, which is also just X is equal to Y. And then I think that's it, right? Those are the only equations that don't have Z's in them. So then I said, okay, if an equation does have a Z coordinate, set it equal to 0. So like this guy here has a Z, so we're going to set it equal to 0. We're going to let Z equals 0 here, and that's going to give me Y squared is equal to 4. Square root, you get plus or minus. Plus or minus 2 in the square root. That you can graph. You can graph Y equals 2, which is right here. And then Y equals negative 2. So then notice that's going to be this line here. And that's going to be this line here. Okay? And then you have, you also have Y equals 0. I guess we know X has to be positive and Y has to be positive since we're going to be in the first octant. So at this point, you would say, do I want to use this region here, this little triangle here, or this little triangle here? But the top right, because X has to be positive and Y has to be positive. So it's going to have to be, this is my region D right here, that triangle. Okay? See how those tips kind of help out? Okay? All right. Some of you guys were doing it of type 1. Some of you guys were doing it of type 2, because you can actually do both. So if you do type 1, you're going to bound Y by some functions above and X by some scalars. So if I do type 1, you can't do both scalars. That's only for a rectangle. And so let's see why. So I have my little ruler that I'm moving throughout the region. Type 1, I move my ruler in the direction of the y-axis. What's the highest, what bounds y above? Which curve? Y equals 2. Yes, sorry, I'm tripping. Y equals 2, yes. Scared you guys, huh? Maybe I scared myself. What bounds it below? That slanted line, Y equals 1/2 X. So that's what's going to bound it below. Y equals 1/2 X. And then my ruler here is going to move from which X value to which X value? 0 to 4, right? Where those two intersect. Y will equal 2 here when X is equal to 4. And so if you do that, you're going to have your bounds where Y will be 1/2 X, Y will be 2. Marco, does that make sense why it's not both scalars?
You can still do scalar, but you just do function, right?
I can't do scalar because as I move these my little rulers here, the lowest Y value isn't always the same Y value. It differs depending on where my X is located. Because if I bound Y below by a scalar, let's say I bound it below by 0, then that means that these guys will always be able to stretch all the way down to 0.
The thing is, this of the state is like 1/2, so you can just do a rectangle and then the whole thing is function.
Oh, okay. I see what you mean. So what he's saying is that
can I just do a rectangle and then divide my integral by 2, since that's just half of it? And the answer is you gotta be careful, because what you're doing is you're doing the volume. There's a surface above here. You're assuming the surface is symmetric above that rectangle.
It is symmetric because of this cylinder. Because it's like y squared plus z squared equal 4. It's a cylinder.
Well, the-
it must be symmetric.
The cylinder, let me see here, the cylinder is doing something like this, right? So this region, this surface above here won't be the same volume as it is up here, because it's curved. Yeah, we'll look at the 3D part in a little bit. But yes, that's a good point. You bring up good points that are gonna affect you guys later on, okay? Just because your region's symmetric here, you gotta keep in mind the surface that's above it, because that affects it. You can't just think it's half of it or double of it. Okay, but there are some properties where we will be able to do something like that, which will come after this example. Okay. Yes. Good point. Okay, we'll sketch all this out and then we'll revisit that. Okay, so x goes from 0 to 4, right? If it's of type 2. If it's of type 2, now you're going to bound x by some functions and then y by some scalars. So now in this case, you're going to be going in this direction. Now your ruler's going this way. So x will be bounded above by which function? 2y, because you're going to write it in terms of y. That slanted line. It'll be bounded above by this line, x equals 2y, and then bounded below by this bad boy right here, right? X equals 0. And then my ruler now can move up and down from which y value to which y value? 0 to 2. And so if you set up your integral, it's going to be y goes from 0 to 2, and then x goes from 0 to 2y. All right. Is that kind of what you guys got for your bounds? Yeah. All right, now we got to figure out the function. So let's see. Now let's go into a more sketch here. Let me sketch the surfaces to kind of get an idea. All right, this is the part that's usually the harder part. Let's see. All right, so we have a cylinder that's missing x, so it's going to be free in the x direction. So on the YZ plane, what does this look like on the YZ plane? Circle of radius 2. I'm just going to circle like this. So it's a circle of radius 2. And it's going to shoot out towards the x direction, since that's the free variable. It shoots out like this. That's it. Okay. And then we have this plane here, which is kind of hard to draw, but it's this line that we said has slope 1/2. That's 2 here, so this is 1. So it has slope 1/2. So it's that line that we drew there is this line that's kind of going out like this. And there's a plane that goes right above it, because it's missing the z variable, so it's free in the z direction. So if you guys can picture like that cylinder being sliced, like that. Okay. And then everything else says it has to be in the first pocket. So, oh god, let's see that. So it's gonna be like this weird, stop right here. It's this part of the cylinder. It's in the first octant. It's back there. So it's like this piece of the cylinder right here. Maybe you can see it. This is the cylinder. Yeah. It's like my water bottle. No, I can show. I sliced it right here. It's just I sliced it right here. It's this part of the water bottle. I think so because you're bounded by x equals 0. You're bounded by x is equal to 0, which is the x equal to 0 is the zy plane. Zy plane. So the back of it is flat. Okay.
And then wouldn't there be a slice on the very bottom of it on the XY plane so that it wouldn't involve anything under the XY plane?
The bottom of it, let me see. Oh shit, you guys are right. There is hold on. This looks like it goes farther than 2, but it doesn't really go farther than 2. It's supposed to be the cylinder intersects it. My sketch is messed up, yeah. The cylinder is supposed to go like this. Because it's a triangle below it. It's a triangle below it. Okay? So there's a triangles below it, and above it is just that part of the water bottle. Okay? All right, you don't need a perfect sketch. You just need to know what my volume is between the XY plane, which is always that region, and the surface, right? The surface is going to be the surface of this cylinder. And as I mentioned, it's usually the equation that has z in it. But you have to write it as a function. So I need to get this equation so that I can write it like this. Okay? So notice that that's my surface here. Z squared is equal plus y squared is equal to 4. So we have to get z by itself. So minus the y squared, square root both sides. You get plus or minus square root, but because we're in the first octant, z will be positive. And so this is the function you're integrating, which was not even listed there for you. That's why this one's hard. Okay? So you really have to put it together. So that's the function that you're going to be integrating with. And this is step 1. Step 2. Why would you prefer to do one over the other? Think of the part where now you have to integrate. Okay. Which one do you want to avoid? If you start with this one, you have to integrate this guy here. There's no outside y to help you with the u set. So you're gonna have to do trig substitution. Okay. So this one requires trig sub. But if you do this one, this whole big old thing is a flat constant because there's no x's in it. So you can pull it out. And then you can integrate with respect to x. And then now the y's are going to show up. And you'll be able to avoid these trig substitution. I'm not going to have you guys do it, but you keep going. This one you can actually avoid. You can avoid trig substitution. You can avoid trig sub. So as you're doing these problems and you get your regions and you have it all set up, you get here and you're like, F. I don't want to do this. Maybe I don't want to do partial fractions or something, right? So then you're going to say, please, can I do is my region of the other type? So I can do it the other way. Yeah, that's it.
How come the type 2, after you pull that out and then you're integrating with respect to y, and you have to go through that square root anyway?
Let's do the first few steps.
So you guys can see it. Let's do the first two steps. Let's do the first two steps, just so you guys can see it. So we try doing the first two steps. Y goes from 0 to 2. And x goes from 0 to y. Dx dy. All right, so this is a constant in terms when we're doing it with respect to x. So we're going to pull it out. Pull out that constant. And so then we're going to integrate 1 dx dy. All right? Or let me actually go like this. From where x will go from 0 to 2y. Let's see where this takes us. Yeah, we got this guy hiding out here as a constant. And then now in here, what's the antiderivative of 1? Just x from 0 to 2y. We got this guy here. What happens when you plug in these bounds? What do we get? You just get a 2y, right? So then notice that now you just have a 2y that got pulled out. And now you're integrating this. Now u sub comes to the rescue. Yeah. So now u sub. Y, u equal the whole thing inside the square root. Okay. And then so on. And so on. We won't finish it. But yeah, that's what it'll be. Way easier. Okay, so far these problems are, oh yeah, Jacob.
How many get problems? Or will it just be easy to do?
There might be some where you have to set up the, because that's going to be sketching regions, yeah, stuff like that. Stuff that's like new to this class. Yeah. You already been tested on the integration, so I'm not going to give you hella of those. Okay? Also, I don't want to grade them. There will be some though. Expect to do integral stuff. Okay, so far every single problem we've done, the regions have been of both type 1 and type 2. Okay? Because what if this one was a type 1, but then when I try to do type 2, it actually doesn't really work out in my favor, and it gets a little bit nasty. So I want to look at some properties, show you guys some properties that you'll be able to use so that you can try to force a type 2 to happen so that you don't, so that way you can avoid trig-sum or something else. So let's look at some properties real quick. Yeah, this is a good problem here. I'm going to show you guys that. All right, just a few properties, not too many. Properties of double integrals. So we look at 3 of them. All right, first one is if your region D can be composed as a union of 2 other regions, then if I want to do a double integral over that region D, let me give you an example before I show you the result. It's somewhat relevant. Yeah, let's take a look. So let's say this is the region right here. It's a small circle and a bigger circle outside of it like that. Okay? Let's say you wanted to see if it was a type 1 or a type 2. Okay? Let's do type 1 first. If I have my ruler
and I have it right here, what's the lowest y can be, and what's the lowest, what's the biggest y can be? Inner circle and outer circle will tell me that, right? But notice that if I move my ruler now outside of the smaller circle, now the lowest bound for y is no longer the smaller circle. Okay? So technically, this whole region in itself is not of type 1. And for a similar argument, when I go sideways, x will be bounded below by 0 here, but then bounded below by the small circle. So this region is neither of type 1 nor type 2. So what you're going to want to do, if I want to make it of type 1, I'm going to split it up into 2 separate regions and call this region D1 and then call this region D2. Okay? And then remember, there's a surface above here, right? The surface of F. The volume I'm looking for is just going to be the volume above D1 plus the volume above D2. And so it turns out that when I want to do this integral here, and I can find, if I can split up my region D as a union of 2 other regions, it's just going to be the same integral of this over D1 plus the same function, but over D2. So unfortunately, you might be able to avoid a nasty trig sum, but then you're going to produce 2 separate integrals. So there's like the good news, bad news kind of situation. Property number 2 is for a region D. We have that if I want to find the area of that region D, let's go back to this region, okay? And I wanted to find the area of this, the area of just this, the circle here, this arc here. And let's say my surface was just a plane above it of height 1. What would be the volume of this solid if the plane was just levitated 1 unit above it? What would be the volume of it? It would be the area of the base times the height, which is just 1. So it's just the area of the base, right? So that's what this property says. That the area of the region is just the double integral over the region of the function 1, where z is equal to 1. That's for any region, as long as you just integrate the function 1. Because I have a visual here. Because if you have your region here, whatever it looks like. Oh, come on, dude. You need to be gentle with it. And I put a plane where z is equal to 1. If I have this plane like this, z is equal to 1. Then when I'm right above it, it's literally just that same region. And so the volume of that will just be the area of the base times the height 1, which is just the area of the base.
And so is this just another way to do what we were doing in Calc 1 and 2, like finding area under multiple curves?
Yeah, yeah. You'll see that when you do this integral, it's just literally the same Calc 1 integral that you figured out. And then the last one is we kind of used this already in the rectangles, but I'm going to generalize it. So for any region D, the average value of a function z equals f of xy is going to be, so the average z value is the same thing we did last time. It's going to be the double integral over a region D of the function.
but instead that result, you're going to divide it by the area of the region. But now this is no longer a rectangle. This could be any region. Sometimes to find this area though, you might need a Calc 1 integral to find it. Yeah, it's area under some curve. So this one's very handy. Okay? All right. That's some practice problems that are going to kind of encompass everything a bit. I think number one's a little confusing. So number one, basically just set up the integrals. Okay? So set up the integrals so that one integral is of type 1 and the other integral is of type 2. You might need to use property 1 for one of those. Okay? And then problems number 2 are the opposite of what you've been doing. I gave you the setup of an integral. I want you to go backwards, and I want you to use the setup to deduce what the regions is supposed to look like. Find the region, and then rewrite it of the other type. Okay? I'm gonna say that again. So I gave you an integral that's set up of a certain type. Let's say it's type 1. You're going to use the information of that to deduce what the region is supposed to look like on the xy plane. Then rewrite the integral so that it's of the other type. Okay? And then but the back two are just like everything we've been doing so far. All right. So let's see. Work these out with your classmates. Solutions will be posted in the notes. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Derek, can you do one? Yes. 1, 2. All right, here you go. Camera.